Hello everyone. In this session, some of the previous MSc entrance exam questions of infinite series are going to be discussed. So first, these problems are displayed here. So total there are 10 questions. Just go through it and see the solutions. Okay, so here we go. Let's move on to the solutions of this. And here is the first question. If the series sigma n converges, then the sequence an. And we have it, that says if sigma an converges, then limit an must be equal to 0. Alright, therefore the sequence an converges and that converges to 0. So option B is right. A direct problem. Now question number 2. A series is given sigma 1 by k log k all to the power alpha, where alpha is a real number. And log k means, logarithm with respect to natural e. Okay, so we need to check the convergence of this series. So here we use the integral test. Okay, so here, so the integral test says that the series converges if and only if this integral converges. Okay, so we consider this integral 2 to infinity, 1 by x log x all to the power alpha dx. And to find the integral of this, you put log x is equal to some u, then du becomes dx by x. So 1 by x dx becomes du, and it becomes 1 by u to the power alpha. Okay, and see, when x is equal to 2, u becomes log 2, and when x is infinity, u also becomes infinity. All right, so now you find the integral of this. See, 1 by u to the power alpha, the integral of that is going to be 1 by minus alpha plus 1 times u to the power alpha minus 1. Okay, and if alpha is equal to 1, it becomes 1 by u. So whose integral is going to be logarithm of u, right? Whose integral is logarithm of u. So when you apply the limit log 2 to infinity, it becomes infinity. So that is not finite. Okay, so if alpha is equal to 1, the integral is not finite, that becomes infinity. Okay, but if alpha is greater than 1, if alpha is greater than, definitely, there will be a u term in the denominator, and when you apply infinity in the limit, that becomes 0, and you will get a finite quantity. All right, so this integral exists only if alpha is strictly greater than 1. So that is what idea. Okay, so it converges only for all alpha greater than 1. So option D is right, all the other options are false. All right, and now question number 3. Yeah, two series are given. The first series is series sigma sine 1 by n. The other one is 1 2 3 square 4 square plus 3 4 by 5 square 6 square and so on. So let's consider the first one, sine 1 by n. All right, so you divide that series by 1 by n. So sine 1 by n by 1 by n, and you take the limit, and you will get a finite limit here. So actually this is a limit comparison test, and here we take bn as 1 by n and an is sine 1 by n. So when we divide and when we take the limit, we get a finite quantity. And here the idea is that both series will have the same characteristic. So here if sigma 1 by n, we know that it diverges, so definitely sigma sine 1 by n also diverges. All right, so sigma sine 1 by n is convergent. The first statement is wrong, so A is false. Now let's see B. And here an is 2n minus 1 times 2n by 2n plus 1 the whole square times 2n plus 2 the whole square. And here you can notice one thing, that numerator is a polynomial of degree 2 and denominator is again a polynomial of degree 4. So if it's like polynomial in both numerator and denominator, then actually you can again apply the limit comparison test, okay, by taking bn as 1 by n to the power p, where p is going to be the degree of numerator minus degree of the denominator. I mean, you take the modulus of that. Okay, so here the degree of the denominator is 4 and degree of the numerator is 2. So when you subtract that, you will get, p is equal to 2. So 1 by n square is going to be bn. Now you can divide an by bn and you will get, this n square goes to the numerator, and now both numerator and denominator will be of same degree 4. Therefore, to find the limit, it's easy. It's enough to take the leading coefficients. That means the coefficient of n to the power 4, and in the numerator, and that's 2 times 2, so it's 4. Numerator it's 4, and denominator it's 2 square times 2 square. Okay, so that's going to be uh, yeah, 1 by 4 times 1 by 4. So the answer is 1 by 4. Anyway, that's a finite quantity, and sigma bn converges here. We know that, right? Sigma bn converges, and therefore by limit comparison test, sigma an also converges. Okay, so that's all about question number 3. So here the answer is an diverges and bn, I mean the first one diverges and second one is convergent. So a is false and b is true. Option C is right. And see question number 4. An alternating series is given and there is an x here. So it looks like x to the power n by n, right? Modulus of, so you check for the absolute convergence. You take the modulus of that and it becomes a positive time series, and you take the absolute convergence. Okay, since we have an x to the power n by n, it's always better to use the ratio test. So limit n tends to infinity a n plus 1 by a n. So that becomes limit n tends to infinity x to the power n plus 1 by n plus 1 times n by x to the power n. Okay, so when you simplify all these and when you take the limit, you will get modulus of x. So this one converges when, so sigma an converges when modulus of x is less than 1. So that is what the idea. So when mod x is less than 1, it converges. Okay, and now the thing is that you have to check, actually mod x less than 1 means it's all values from minus 1 to 1, and that value does not include minus 1 and 1. Okay, so that has to be checked separately. So when x is equal to minus 1, our series becomes sigma, when x is equal to minus 1, it looks like this: minus 1 minus 1 by 2 minus 1 by 3 minus 1 by 4 and so on. This is what you will get when x is equal to minus 1. First time becomes minus 1, the second time is again negative 1 by 2, third becomes negative, fourth is already negative, and so on. Okay, so this is nothing but negative sigma 1 by n. The series is divergent. Alright, so when x is equal to 1, what happens? Then the series becomes 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus etc. And this is the harmonic alternating harmonic series that converges, right? The standard series, this one converges. Okay, so the actual region of convergence is open interval minus closed interval 1. That means at minus 1 the series does not converge, but at 1 it converges, right? So the answer looks like this: is convergent for whole values of x, that's false. Mod x less than 1 only, that's also not true, because when x is equal to 1, that series is convergent. Is convergent for mod x less than 1, that's true, and the same as d also, right? typo error. Anyway, so here the correct options are C and D. In question number 5, an is equal to sine of 1 by n square. So we need to find the limit of an, and we need to check whether the series converges or not. See, actually here, as n tends to infinity, sine of 1 by n square, that is equal to 0, because 1 by infinity is 0, sine 0 is 0. So the limit of the sequence exists, and that is 0. Okay, since the limit is 0, uh, which means that it has only one limit, therefore the limit supremum and limit infimum must be equal. Okay, and that's equal to 0. Therefore we can say that these two options, B, option A and C, are false, because limit n is equal to 0, and therefore limit supremum and limit infimum must be equal, and that should be equal to 0. Now consider the series sigma a. You choose Bn is equal to 1 by n square and apply the limit comparison test. So limit n tends to infinity an by Bn is equal to limit n tends to infinity sine 1 by n square by 1 by n square. And see, as n tends to infinity, it seems like sine x goes to 0, sine x by x. And that has value 1. Therefore, uh, and this one is a finite quantity. And sigma Bn is convergent, therefore sigma n is also convergent by limit comparison test. Alright, now question number 6. Series sigma n plus 1 by n to the power p is convergent for what values of p? And we can write n plus 1 by n to the power p as n by n to the power p plus 1 by n to the power p. And here one n is cancelled, so sigma 1 by n to the power p minus 1 plus sigma 1 by n to the power p. And we know that the first series converges when p minus 1 is greater than 1, because this one is a p series, right? So when p minus 1 is greater than 1, the first series converges. And for the second series, when p is greater than 1, that converges, right? Therefore, uh, therefore, the common value for which these two series converge is that p must be greater than 2. Alright, so it converges for p greater than 2. Now, question number 7. Four series are given. We need to check which one converges and which one diverges. Okay. Look at the second one first. Option B. Sigma 1 minus 1 by n all the whole square. So there we apply the divergence test. Just take the limit of the nth term. So limit n tends to infinity 1 minus 1 by n the whole square. So as n tends to infinity, 1 by n goes to 0, and the answer is 1, and that's not equal to 0. So the nth term does not go to 0. Therefore, definitely the series diverges. Okay, so the second option is not right. And similarly, the third one, n factorial by n, and that is also n factorial by n means sigma n minus 1 factorial. There again, when you take the limit as n tends to infinity, n minus 1 factorial goes to infinity. So that's not equal to 0. So the nth term diverges. So definitely the series diverges. So C is not the option. And now option D. In option D, there again you take the limit uh, of the nth term 2 to the power n by log n 1 by 1 plus 1 by n the whole to the power n. And this one has got a finite limit 1 plus 1 by n all to the power n. This one is a standard limit, and that's E. Alright, and now limit n tends to infinity 2 to the power n by log n. So just compare these two terms. One is an exponential function in the numerator. The denominator we have a logarithmic function. Okay, so since the numerator is exponential, that goes to infinity faster than the denominator. Therefore it goes to infinity. Actually this 2 to the power n by log n goes to infinity, and that's not equal to 0. So by divergence test, this series also diverges. So D is also not the answer. Now consider option 1. And here mode cosine plus mode sin n by n. And here actually we use Dirichlet's test. Okay, and there the condition is that if a sequence Bn is decreasing and converges to 0, and uh, Sn equal to a1 plus a2 plus extra an, that means the partial sum sequence is bounded, then we can say that sigma a and bn is convergent. So it uh, it gives an idea about the convergence of the product of two series, right? Sigma a and bn. Okay, so one of the term should be decreasing and converges to 0, and for the other one the partial sum should be bounded. And here choose bn as 1 by n, and here we have two times mode sin n plus mode cosine, and that can be taken as an, and 1 by n can be taken as bn. So 1 by n decreases and converges to 0, and Sn is the sequence of partial sums: sin 1 plus sin cos 1 plus sin 2 plus cos 2, and so on, sin n plus cosine. See, all these functions are bounded, right? Sin 1 cos 1, I mean sin and cos are bounded functions, and these are positive as well since we take the modulus. Okay, therefore Sn is bounded, we can say. So sequence of partial sum is bounded, the other one converges to 0, therefore the product sigma an times bn definitely converges. Okay, so by Dirichlet's test, this series converges. All right, question number 8. Okay, two series are given, sigma n and sigma bn. Both are convergent series, and it's given that both are positive time series, and an plus bn is not equal to 1. Okay, now based on an and bn, two series are obtained. Okay, so the first one sigma an times 1 minus bn to the power n. The second one, 8 to the power n 1 plus 1 by n to the power 4n by 9 to the power n 1 minus a n plus b n all to the power n. We need to check the convergence of these two series. Alright. Look at the first one, S1. Okay. And here actually as n tends to infinity, both series converges. We know that, right? Sigma n and sigma bn converges. Therefore, the nth time the sequence of uh, an and sequence an and bn converges to 0 by definition, right? So as n tends to infinity, we know that bn goes to 0 since sigma bn is convergent. Bn goes to 0, and we can write, therefore, and bn is a positive time series as well. Therefore, as n tends to infinity, the values of bn should be in between 0 and 1. Definitely, we can say, I mean, okay, the value of bn should be in between 0 and 1. Therefore, 1 minus bn also lies between 0 and 1. So when you take the power of that, again that will be in 0 1. All right. Therefore, and you multiply a quantity with a quantity in between 0 and 1. So definitely you can say that an times 1 minus bn to the power n is less than n, because this one is a quantity which is less than 1. All right. And the right hand side, an is a convergent series. Therefore, by direct comparison test, we can say that sigma an times 1 minus bn to the power n an is convergent, right? So the first series converges. So S1 is true. S1 is true. Now consider the second one, and here you can observe one thing that uh, every term has got a power n. Therefore, it's always better to apply Cauchy's root test. Take an all to the power 1 by n, so that it becomes limit n tends to infinity 8 by 9 1 plus 1 by n to the power 4 divided by 1 minus a n plus b n. So as n tends to infinity, this one will be 1, and a n and b n goes to 0. Therefore, this one also will be 1. So the answer is going to be 8 by 9, which is less than 1. Therefore, by Cauchy's root test, sigma a n converges. Right? So both the series converges here. Okay, that also right. So both S1 and S2 are true. Option A is right. Now look at question number 9. It's given that an is a positive time sequence and sigma an converges. Alright. So consider the following sequence. Sigma e to the power an by n to the power 3 by 2. Alright. And there in the first case, there is an easy way that you can choose Vn is 1 by n to the power 3 by 2. Okay. And take the apply limit comparison test. Limit n tends to infinity un by Vn. Okay. When you take that, you will get e to the power n as n tends to infinity. Since sigma n converges, limit n is equal to 0. So you'll get e to the power 0, that's equal to 1. So that's a finite quantity. Okay, so both series, sigma un and sigma vn, will be having the same property. Okay, since we know that it's a p series, so sigma vn converges. Therefore, sigma un also converges. So the first one, uh, it converges. That is right. Now look at S2. You just take limit n tends to infinity mod sin an by an. We know that as n tends to infinity, an goes to 0. So sin it looks like uh, limit some extends to 0 sin x by x. It seems like this, right? So that's going to be 1. Okay. So here by divergence test, this is not equal to 0. Therefore, this series diverges by divergence test. So this one is false. So S1 is true and S2 is false. Option B is right. Now, question number 10. Which of the following is true? Okay. So, see, the first three terms is the finite sum of a geometric series. And we have that formula 8 plus a r plus etc plus a r to the power n minus 1 is 8 times 1 minus r to the power n by 1 minus r. Okay, so first you consider this one 1 plus 1 by 2 plus 1 by 2 square plus etc plus 1 by 2 to the power n minus 1. And here the common ratio is 1 by 2 and the first term is 1. Therefore, we can write 1 minus 1 by 2 all to the power n by 1 minus 1 by 2. We can simplify it. Okay. And, 1 minus 1 by 2 is 1 by 2. That goes to the numerator. So, we'll get 2 minus 2 times 1 by 2 to the power n. And you will get 2 minus 1 by 2 to the power n minus 1. Okay. So, this is the sum of first 10 terms. And if you consider it's like 1 plus 1 by 2 plus etc plus 1 by 2 to the power n, then just replace this n minus 1 by n, so that it becomes 2 minus 1 by 2 to the power n. And we can say that this is strictly less than 2, right? So 1 plus 1 by 2 plus etc plus 1 by 2 to the power n will be less than 2. Okay, so we can say that C is true. This is always less than 2. So option C is right. Okay, and for the first one, for B, you put n is equal to 2 and see what happens here. And you take the first two terms of the left side 1 plus 1 by 2 and put n is equal to 2 here. So this is what you will get when n is equal to 2. 1 plus 1 by 2 is greater than 2 plus 1 by 2 minus 1. That means 3 by 2 is greater than 3, and that's false, right? And that's false. Therefore option B is false. Option B is false. Similarly, for the first one, you can take the first four terms 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube, and that is less than 2 minus 1 by 5. Yeah, put n is equal to 4 there. Okay, so take the first four terms and 1 minus 1 by 5. That's what you'll get. And when you simplify, you can see that 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 is less than 2 minus 1 by 5. When you simplify, you'll get 15 by 8 is less than 9 by 8, or you'll get 75 is less than 72, and that's not a true statement. Therefore, uh, and here you can observe one thing, that when n is equal to 1, 2 and 3, this result is true, but after that, uh, the result is false. Okay, so Yeah, so A is also false. So only the correct option is C. D is also false. So C is the correct option. All right. Okay, so that's it for this question. Okay, so let's wind up. Thank you. Bye.